All right, hello everybody. Welcome back in. My name is Michael, and thanks so much for joining me again today. We're going to be jumping back into Introduction to Algorithms CLRS, 4th edition, more specifically Chapter 4 today. We're going to be reading this one. Let's get started. Our Corman Introduction to Algorithms 4th edition, Chapter 4, Divide and Conquer. The divide and conquer method is a powerful strategy for designing asymptotically efficient algorithms. We saw an example of divide and conquer in section 2.3.1 when learning about merge sort. In this chapter, we'll explore applications of the divide and conquer method and acquire valuable mathematical tools that you can use to solve the recurrences that arise when analyzing divide and conquer algorithms. Recall that for divide and conquer, you solve a given problem instance recursively. If the problem is small enough, the base case, you just solve it directly without recursing. Otherwise, the recursive case, you perform 3 characteristic steps. Divide the problem into one or more subproblems that are smaller instances of the same problem. Conquer the subproblems by solving them recursively. Combine the subproblem solutions to form a solution to the original problem. A divide and conquer algorithm breaks down a large problem into subproblems, which themselves may be broken down into even smaller subproblems, and so forth. The recursion bottoms out when it reaches a base case, and the subproblem is small enough to solve directly without further recursing. Recurrences. To analyze recursive divide and conquer algorithms, we'll need some mathematical tools. A recurrence is an equation that describes a function in terms of its value on other, typically smaller arguments. Recurrences go hand in hand with the divide and conquer method because they give us a natural way to characterize the running times of recursive algorithms mathematically. You saw an example of a recurrence in section 2.3.2 when we analyzed the worst case running time of merge sort. For the divide and conquer matrix multiplication algorithms presented in section 4.1 and 4.2, we'll derive recurrences that describe their worst case running times. To understand why these two divide and conquer algorithms perform the way they do, you'll need to learn how to solve the recurrences that describe their running times. Section 4.3 through 4.7 teach several methods for solving recurrences. These sections also explore the mathematics behind recurrences, which can give you strong intuition for designing your own divide and conquer algorithms. We want to get to the algorithms as soon as possible. So let's just cover a few recurrence basics now, and then we'll look more deeply at recurrences, especially how to solve them, after we see the matrix multiplication examples. The general form of a recurrence is an equation or inequality that describes a function over the integers or reals using the function itself. It contains 2 or more cases depending on the argument. If a case involves the recurrence invocation, the function on different, usually smaller inputs, it is a recursive case. If a case does not involve a recursive invocation, it is a base case. There may be a 0, 1, or many functions that satisfy the statement of the recurrence. The recurrence is well defined if there is at least one function that satisfies it, and ill-defined otherwise. Algorithmic recurrences. We'll be particularly interested in recurrences that describe the running times of the divide and conquer algorithms. A recurrence, T of n, is algorithmic if, for every sufficiently large threshold, constant n naught that is greater than 0, the following 2 properties hold. For all values that are less than that initial n naught, we have some recurrence that is constant. For all values of n that are greater than or equal to that initial n naught, every path of recursion terminates in a base case within a finite number of recursive invocations. Similar to how we sometimes abuse asymptotic notation, see page 60, when a function is not defined for all arguments, we understand that this definition is constrained to values of n for which T of n is defined. Why would a recurrence T of n that represents a correct divide and conquer algorithm's worst case running time satisfy these properties for all sufficiently large threshold constants? The first property says that there exist constants C1, C2 such that 0 is less than C1, which is less than or equal to the recurrence T sub n, which is less than or equal to C of 2, for all n values that are less than that initial n naught. For every legal input, the algorithm must output the solution to the problem it's solving in finite time. See section 1.1. Thus, we can let C1 be the minimum amount of time to call and return from a procedure, which must be positive because machine instructions need to be executed to invoke a procedure. The running time of the algorithm may not be defined for some values of n if there are no legal inputs of that size, but it must be defined for at least one, or else the algorithm doesn't solve any problem. Thus, we can let C of 2 be the algorithm's maximum running time on any input size of n which is less than n naught, where n naught is the sufficiently large value that the algorithm solves at least one problem of size less than n naught. The maximum is well defined since there are at most a finite number of inputs of size less than n naught, and there is at least one if n naught is sufficiently large. Consequently, the recurrence t of n satisfies the first property. If the second property fails to hold for t of n, then the algorithm isn't correct because it would end up in an infinite recursive loop or otherwise fail to compute a solution. Thus, it stands to reason that a recurrence for the worst case running time of a correct divide and conquer algorithm would be algorithmic. Conventions for recurrences. We adopt the following convention. Whenever a recurrence is stated without an explicit base case, we assume that the recurrence is algorithmic. That means you're free to pick any sufficiently large threshold constant, n naught, for the range of base cases where t of n, the recurrence, is equal to theta of 1. Interestingly, the asymptotic solutions of the most algorithmic recurrences you're likely to see when analyzing algorithms don't depend on the choice of threshold constant, as long as it's large enough to make the recurrence well defined. Asymptotic solutions of algorithms divide and conquer recurrences also don't tend to change when we drop any floors or ceilings in a recurrence defined on the integers to convert it to a recurrence defined on the reals. Section 4.7 gives a sufficient condition for ignoring floors and ceilings that applies to most of the divide and conquer recurrences you're likely to see. Consequently, we'll frequently state algorithmic recurrences without floors and ceilings. Doing so generally simplifies the statement of the recurrences as well as any math that we do with them. You may sometimes see recurrences that are not equations, but rather inequalities, such as the recurrence t of n is less than or equal to 2t of n divided by 2 plus theta of n. Because such a recurrence states only an upper bound on t of n, we express its solution using O notation rather than theta notation. Similarly, if the inequality is reversed to t of n is greater than or equal to the 2 times t of n divided by 2 plus theta of n, because the recurrence only gives a lower bound on t, then we use omega notation in its solution. Divide and conquer and recurrences. This chapter illustrates the divide and conquer method by presenting and using recurrences to analyze two divide and conquer algorithms for multiplying n times n matrices. Section 4.1 presents a simple divide and conquer algorithm that solves a matrix multiplication problem of size n by breaking it into 4 subproblems of size n divided by 2, which it then solves recursively. The running time for the algorithm can be characterized by the recurrence of t of n equals to 8 times t of n divided by 2 plus theta of 1, which turns out to have a solution of t of n is equal to theta of n cubed. Although the divide and conquer algorithm is no faster than the straightforward method that uses a triply nested loop, it leads to an asymptotically faster divide and conquer algorithm due to the V-Strassen, which we'll explore in section 4.2. Strassen's remarkable algorithm divides a problem of size n into 7 subproblems of size n over 2, which it solves recursively. The running time of Strassen's algorithm can be described by the recurrence t of n equals to 7 times t of n over 2 plus theta n squared, which has the solution of t of n equals to theta of n to the power of log 7, which is equal to big O of n to the power of 2.81. Strassen's algorithm beats the straightforward looping method asymptotically. These two divide and conquer algorithms both break a problem of size n into several subproblems of size n divided by 2. Although it is common when using divide and conquer for all of the subproblems to have the same size, that isn't always the case. Sometimes it's productive to divide a problem of size n into subproblems of different sizes, and then the recurrence describing the running time reflects the irregularity. For example, consider a divide and conquer algorithm that divides a subproblem of size n into one subproblem of size n over 3 and another size of 2n over 3, taking theta of n time to divide the problem and combine the solutions to the subproblem. Then the algorithm's running time can be described by the recurrence t of n is equal to t of n over 3 plus t of 2n over 3 plus theta of n, which turns out to have the solution t of n equals to theta n log n. We'll see an algorithm in chapter 9 that solves a problem of size n by recursively solving a subproblem of size n over 5 and another of size 7n over 10, taking theta n time for the divide and combine steps. Its performance satisfies the recurrence t of n is equal to t of n over 5 plus t of 7n over 10 plus theta n, which has solution T of n is equal to theta n. Although divide and conquer algorithms usually create subproblems with sizes of constant fraction of this original problem size, that's not always the case. For example, a recursive version of linear search, see exercise 2.1-4, creates just one subproblem with one element less than the original problem. Each recursive call takes constant time, plus the time to recursively solve a subproblem with one less element, leading to the recurrence. T of n is equal to T of n less than 1 plus theta of 1, which has a solution T of n equal to theta of n. Nevertheless, the vast majority of efficient divide and conquer algorithms solve subproblems that are a constant fraction of the size of the original problem, which is where we'll focus our efforts. Solving recurrences. After learning about divide and conquer algorithms for matrix multiplication in section 4.1 and 4.2, we'll explore several mathematical tools for solving recurrences. That is, for obtaining asymptotic theta, O, and omega bounds on their solutions. We want simple to use tools that can handle the most common occurring situations, but we also want general tools that work perhaps with a little more effort for less common cases. This chapter offers 4 methods for solving recurrences. In the substitution method, section 4.3, you guess the form of a bound and then use mathematical induction to prove your guess correct and solve for constants. This method is perhaps the most robust method for solving recurrences, but it also requires you to make a good guess and to produce an inductive proof. The recursion tree method, section 4.4, models the recurrence as a tree whose nodes represent the costs incurred at various levels of the recursion. To solve the recurrence, you determine the costs at each level and add them up, perhaps using techniques for bounding summations from section 8.2. Even if you don't use this method to formally prove a bound, it can be helpful in guessing the form of the bound for use in the substitution method. The master method, section 4.5 and 4.6, is the easiest method when it applies. It provides bounds for recurrences of the form T of n is equal to A times T of n over B plus F of n, where A is greater than 0 and B is greater than 1 are constants, and F of n is a given driving function. This type of recurrence tends to arise more frequently in the study of algorithms than any other. It characterizes a divide and conquer algorithm that creates A subproblems, of each of which is 1 over B times the size of the original problem, for using F of n time for the divide and combine steps. To apply the master method, you need to memorize 3 cases, but once you do, you can easily determine the asymptotic bounds on running times for many divide and conquer algorithms. We can use the divide and conquer method to multiply square matrices. If you've seen matrices before, then you've probably known how to multiply them. Otherwise, you should read section D.1. Let A equal to A of I k and B equal to B of jk. B square n times n matrices. The matrix product C equals to A times B is also an n by n matrice, wherefore I and j are equal to 1, 2, all the way up to some value n, and the ij entry of C is given by C of ij is equal to the sum of all values, indices 1 through n, of the matrix A sub ik times B sub kj, right? Generally, we'll assume that the matrices are dense, meaning that most of the n squared entries are not 0, as opposed to sparse, where most of the n squared entries are 0, and the non-zero entries can be stored more compactly than in an n by n array. Computing the matrix C requires computing n squared matrix entries, each of which is the sum of n pairwise products of input elements from A and B. The matrix multiply procedure implements this strategy in a straightforward manner, and it generalizes the problem slightly. It takes as input 3 n by n matrices A, B, and C, and it adds up the matrix products A times B to C, storing the result in C. Thus, it computes C is equal to C plus A times B, instead of just C equals A times B, if only the product A times B is needed. Just initialize all n squared entries of C to 0 before calling the procedure, which takes an additional theta of n squared time. We'll see the cost of matrix multiplication asymptotically dominates this initialization cost. The pseudocode for matrix multiply works as follows. The for loop of lines 1 through 4 computes the entries of each row I, and within a given row I, the for loop of lines 2 through 4 computes each of the entries C of I, j for each column j. Each iteration of the for loop of lines 3 through 4 adds in one more term of equation 4.1. Because each of the triply nested for loops runs for exactly n iterations and each execution of line 4 takes constant time, the matrix multiply procedure operates in theta of n cubed time. Even if we add in the theta n squared time for initializing C to 0, the running time is still theta n cubed. Simple divide and conquer algorithm. Let's see how to compute the matrix product A times B using divide and conquer for n greater than 1. The divide step partitions the n by n matrices into 4 n over 2 by n over 2 submatrices. We'll assume that n is an exact power of 2, so that as the algorithm recurses, we are guaranteed that the submatrix dimensions are integers. Exercise 4.1-1 asks you to relax this assumption. As with matrix multiply, we'll actually compute C equals to C plus A times B. But to simplify the math behind the algorithm, let's assume that C has been initialized to the 0 matrix, so that we are indeed computing C equals to A times B. The divide step views each of the n by n matrices A, B, and C as 4 n over 2 by n over 2 submatrices. Equations 4.5 through 4.8 involve 8 n over 2 by n over 2 multiplications and 4 additions of n over 2 by n over 2 submatrices. As we look to transform these equations to an algorithm that can be described with pseudocode or even implemented for real, there are two common approaches for implementing the matrix partitioning. One strategy is to allocate temporary storage to hold matrix A's 4 submatrices A11, A12, A21, and A22, and B's 4 submatrices B11, B12, B21, and B22. Then copy each element in A and B to its corresponding location in the appropriate submatrix. After the recursive conquer step, copy the elements in each of C's 4 submatrices, C11, C12, C21, and C22, to their corresponding locations in C. This approach takes theta n squared time, since 3 times n squared elements are copied. The second approach uses index calculations and is faster and more practical. A submatrix can be specified within a matrix by indicating where within the matrix the submatrix lies without touching any matrix elements. Partitioning a matrix, or recursively a submatrix, only involves arithmetic on this location information, which has constant size independent of the size of the matrix. Changes to the submatrix elements update the original matrix, since they copy the same storage. Going forward, we'll assume that index calculations are used and that partitioning can be performed in theta of 1 time. Exercise 4.1-3 asks you to show that it makes no difference to the overall asymptotic running time of the matrix multiplication. However, whether the partitioning of matrix uses the first method of copying or the second method of index calculation. But for other divide and conquer matrix calculations, such as matrix addition, it can make a difference, as exercise 4.1-4 asks you to show. The procedure, matrix multiplication recursively, uses equations 4.5 through 4.8 to implement a divide and conquer strategy for 4-square matrix multiplication. Like matrix multiply, the procedure matrix multiply recursive computes C equals to C plus A times B, since, if necessary, C can be initialized to 0 before the procedure is called to compute only C equals to A times B. As we walk through the pseudocode, we'll derive a recurrence to characterize its running time. Let T of n be the worst case time to multiply two n by n matrices using this procedure. In the base case, when n equals 1, line 3 performs just the one scalar multiplication and one addition, which means that T of 1 equals to theta of 1. As in our convention for constant base cases, we can omit the base case in the statement of the recurrence. The recursive case occurs when n is greater than 1. As discussed, we'll use index calculations to partition the matrices in line 6 taking theta 1 time. Lines 8 through 15 Recursively call matrix multiply recursive a total of 8 times. The first 4 recursive calls compute the first terms of equations 4.5 and 4.8, and the subsequent 4 recursive calls compute and add in the second terms. Each recursive call adds the product of a submatrix of A and a submatrix of B to the appropriate submatrix of C in place, thanks to index calculations. Because each recursive call multiplies to n over 2 by n over 2 matrices, thereby contributing to t of n over 2 to the overall running time. The time taken by all 8 recursive calls is 8 times t of n over 2. There is no combined step because the matrix C is updated in place. The total time for the recursive case, therefore, is the sum of the partitioning time and the time for all recursive calls, or theta of 1 plus 8 times t of n over 2. Thus, omitting the statement of the recursive base case, a recurrence for the running time of matrix multiply recursive is t of n equals to 8t of n over 2 plus theta of 1. As we'll see from the master method in section 4.5, recurrence 4.9 has the solution t of n equals to theta n cubed, which means that it has the same asymptotic running time as the straightforward matrix multiply procedure. Why is the theta n cubed solution to this recurrence much larger than the theta n log n solution to the merge sort recurrence in 2.3 on page 41? After all, the recurrence for merge sort contains a theta n term, whereas the recurrence for recursive matrix multiplication contains only a theta of 1 term. Let's think about what the recursion tree for recurrence 4.9 would look like as compared with the recursion tree for merge sort illustrated in figure 2.5 on page 43. The factor of 2 in the merge sort recurrence determines how many children each tree node has, which in turn determines how many terms contribute to the sum at each level of the tree. In comparison, for the recurrence 4.9 for matrix multiply recursive, each internal node in the recursion tree has 8 children, not 2, leading to a bushier recurrence tree which has more leaves despite the fact that the internal nodes are each much smaller. Consequently, the solution to recurrence 4.9 grows much more quickly than the solution to recurrence 2.3, which is born out of the actual solutions theta of n cubed versus theta n log n. 4.2. Strasson's algorithm for matrix multiplication. You might find it hard to imagine that any matrix multiplication algorithm could take less than theta n cubed time, since the natural definition of matrix multiplication requires n cubed scalar multiplications. Indeed, many mathematicians presumed that it was not possible to multiply matrices in little o of n cubed time, until 1969 when V. Strasson published a remarkable recursive algorithm for multiplying n by n matrices. Strasson's algorithm runs in theta n to the power of log 7 time, since log 7 is equal to about 2.8073549, ... Strasson's algorithm runs in O of n to the power of 2.81 time, which is asymptotically better than the theta n cubed time. Matrix multiply and matrix multiply recursive procedures. The key to Strasson's method is to use the divide and conquer idea from the matrix multiply recursive procedure, but make the recursion trees less bushy. We'll actually increase the work for each divide and combine step by a constant factor, but the reduction in business will pay off. We won't reduce the bushiness from the 8-way branching of recurrence all the way down to the 2-way branching of recurrence, but we'll improve it just a little, and that will make a big difference. Instead of performing 8 recursive multiplications of n over 2 by n over 2 matrices, Strasson's algorithm performs only 7. The cost of eliminating one matrix multiplication is several new additions and subtractions of n over 2 by n over 2 matrices, but still only a constant number. Rather than saying additions and subtractions everywhere, we'll adopt the common terminology of calling them both additions because subtraction is structurally the same computation as addition except for a sign change. To get an inkling how the number of multiplications might be reduced, as well as why reducing the number of multiplications might be desirable for matrix calculations, suppose that you have two numbers x and y, and you want to calculate the quantity x squared minus y squared. The straightforward calculation requires 2 multiplications to square x and y, followed by 1 subtraction, which you can think of as a negative addition. But let's recall the old algebra trick of x squared minus y squared is equal to x squared minus xy plus xy minus y squared, which is abstracted out to this, which equals to x plus y times x minus y. Using this formulation of the desired quantity, you could instead compute the sum of x plus y and the difference of x minus y and then multiply them, requiring only a single multiplication and two additions. At the cost of an extra addition, only one multiplication is needed to compute an expression that looks as if it requires two. If x and y are scalars, there's not much difference. Both approaches require three scalar operations. If x and y are large matrices, however, the cost of multiplying outweighs the cost of adding, in which case the second method outperforms the first, although not asymptotically. Strasson's strategy for reducing the number of matrix multiplications at the expense of more matrix additions is not at all obvious, perhaps the biggest understatement in this book. As with matrix multiply recursives, Strasson's algorithm uses the divide and conquer method to compute C equals to C plus A times B, where A, B, and C are all n by n matrices, and n is an exact power of 2. Strasson's algorithm computes the four submatrices C11, C12, C21, and C22 of C from equations 4.5 through 4.8 on page 82 in 4 steps. We'll analyze costs as we go along to develop a recurrence T of n for the overall running time. Let's see how it works. If n equals 1, the matrices each contain a single element. Perform a single scalar multiplication and the single scalar addition, as in line 3 of matrix multiply recursive, taking theta of 1 time, and return. Otherwise, partition the input matrices A and B and output matrix C into n over 2 by n over 2 submatrices, as in equation 4 by 2. This step takes theta of 1 time by index calculation, just as in matrix multiply recursive. Step 2. Create n over 2 by n over 2 matrices, S1, S2, all the way up through S10, each of which is the sum or difference of two submatrices from step 1. Create and zero the entries of 7 n over 2 by n over 2 matrices, P1, P2, all the way through P7, to hold 7 n over 2 by n over 2 matrix products. All 7 matrices can be created, and the Pi initialized in theta n squared time. Step 3. Using the submatrices from step 1 and the matrices S1, S2, all through S10, created in step 2, recursively compute each of the 7 matrix products, P1, P2 through P7, taking 7 T of n over 2 time. Update the 4 submatrices C11, C12, C21, and C22 of the result matrix C by adding or subtracting various Pi matrices, which takes theta n squared time. We'll see the details of steps 2 through 4 in a moment, but we already have enough information to set up a recurrence for the running time of Strasson's method. As is common, the base case in step 1 takes theta 1 time, which we'll omit when stating the recurrence. When n is greater than 1, steps 1, 2, and 4 take a total of theta n squared time, and step 3 requires 7 multiplications of n over 2 by n over 2 matrices. Hence, we obtain the following recurrence for the running time of Strasson's algorithm: 7 times t n over 2 plus theta n squared. Compared with matrix multiply recursive, we have traded off one recursive submatrix multiplication for a constant number of submatrix additions. Once you understand recurrences and the solutions, you'll be able to see why this trade-off actually leads to a lower asymptotic running time. By the master method in section 4.5, recurrence 4.10 has the solution T of n equals to theta n to the power of log 7, which equals to big O of n to the power of 2.81, beating the theta n cubed time algorithms. Now, let's delve into the details. Step 2 creates the following 10 matrices. This step adds or subtracts n over 2 by n over 2 matrices 10 times, taking theta n squared time. Step 3 recursively multiplies n over 2 by n over 2 submatrices 7 times to compute the following n over 2 by n over 2 submatrices, each of which is the sum or difference of products of A and B submatrices. The only multiplications that the algorithm performs are those in the middle columns of these equations. The right-hand column just shows what these products equal in terms of the original submatrices created in step 1, but the terms are never explicitly calculated by the algorithm. Step 4 adds to and subtracts from the 4 n over 2 by n over 2 submatrices of the product C the various pi matrices created in step 3. We start with C11 equals to C11 plus P5 plus P4 minus P2 plus P6. Expanding the calculation on the right-hand side with the expansion of each P sub I on its own line and vertically aligning terms that cancel out, we see the updated C sub 11 equals to, which corresponds to equation 4.5, similarly setting C12 equal to this, updating here, corresponding to equation 4.6, setting C21 equal to this, means that updated to C21 equals to this, corresponds to equation 4.7, finally setting C22 to this, means that updated to C22 equals to, which corresponds to the equation 4.8. Altogether, since we add or subtract n over 2 by n over 2 matrices 12 times in step 4, this step indeed takes theta n squared time. We can see that Strasson's remarkable algorithm comprising steps 1 through 4 produces the correct matrix product using 7 submatrix multiplications and 18 submatrix additions. We can also see that the recurrence 4.10 characterizes its running time. Since section 4.5 shows that this recurrence has the solution t of n equals to theta n to the power of log 7, which is equal to little o of n cubed, Strasson's method asymptotically beats the theta n cubed matrix multiply and matrix multiply recursive procedures. 4.3. The substitution method for solving recurrences. Now that you've seen how recurrences characterize the running times of divide and conquer algorithms, let's learn how to solve them. We start in this section with the substitution method, which is the most general of the 4 methods in this chapter. The substitution method comprises 2 steps. Number 1, guess the form of the solution using symbolic constants. Number 2, use mathematical induction to show that the solution works and find the constants. To apply the inductive hypothesis, you substitute the guessed solution for the function on smaller values, hence the name substitution method. This method is powerful, but you must guess the form of the answer. Although generating a good guess might seem difficult, a little practice can quickly improve your intuition. You can use the substitution method to establish either an upper or lower bound on a recurrence. It's usually best not to try to do both at the same time. That is, rather than trying to prove a theta bound directly, first prove a big O bound, then prove a big omega bound. Together they give you a theta bound. As an example of the substitution method, let's determine an asymptotic upper bound on the recurrence. T of n equals to 2t of the floor of n over 2 plus theta n. This recurrence is similar to the recurrence 2.3 on page 41 for merged sort, except for the floor function, which ensures that t of n is defined over the integers. Let's guess that the asymptotic upper bound is the same t of n equals to O of n log n, and use the substitution method to prove it. We'll adopt the inductive hypothesis that t of n equals to c times n log n for all n that are greater or equal to n naught, where we'll choose the specific constants c is greater than 0 and n naught is also greater than 0, after we see what constraints they need to obey. If we can establish this inductive hypothesis, we can conclude that t of n is equal to O of n log n. It would be dangerous to use t of n equals to O of n log n as the inductive hypothesis because the constants matter, as we'll see in a moment in our discussion on pitfalls. Assume by induction that this bound holds for all numbers, at least as big as O naught and less than n. In particular, therefore, if n is greater than 2 times n naught or equal to it, it holds for floor of n over 2, yielding t of floor of n over 2, which is less than some constant c times the floor of n over 2 times the log of the floor of n over 2. Substituting into recurrence 4.11, hence the name substitution method yields that t of n is less than or equal to 2 times some constant c times the floor of n over 2 times log floor n over 2 plus theta n, which reduces down to t of n is less than or equal to c n log n, where the last step holds if we constrain the constants n naught and c to be sufficiently large that for n greater than or equal to 2 times n naught, the quantity Cn dominates the anonymous function hidden by the theta n term. We've shown that the inductive hypothesis holds for the inductive case, but we also need to prove that the inductive hypothesis holds for the base case of the induction. That is, that T of n is less than or equal to C n log n when n naught is less than or equal to n, which is less than n naught times 2, as long as n naught is greater than 1, a new constraint on n naught. We have log n is greater than 0, which implies that n log n is greater than 0. So let's pick n naught equals to 2. Since the base case of recurrence is not stated explicitly by our convention, T of n is algorithmic, which means that T of 2 and T of 3 are constant, as they should be if they describe the worst case running time of any real program on inputs of size 2 or 3. Picking C equals max of the set T of 2, T of 3 yields T of 2, which is less than or equal to C, which is less than 2 log 2 times C, and T of 3, which is less than or equal to C, which is less than 3 log 3 times C. Establishing the inductive hypothesis for the base cases. Thus, we have T of n is less than or equal to C times n log n for all n that are greater than or equal to 2, which implies that the solution to recurrence 411 is T of n equals to big O n log n. In the algorithms literature, people rarely carry out their substitution proofs to this level of detail, especially in their treatment of base cases. The reason is that for most algorithmic divide and conquer recurrences, the base cases are all handled in pretty much the same way. You ground the induction on a range of values from a convenient positive constant n naught up to some constant n naught prime, which is greater than n naught, such that for n is greater than or equal to n naught prime. The recurrence always bottoms out in a constant size base case between n naught and n prime naught. This example used n prime naught, which is equal to 2 times n naught. This example used n prime naught of 2 n naught. Then it's usually apparent without spelling out the details that with a suitably large choice of the leading constant, such as C for this example, the inductive hypothesis can be made to hold for all values in the range from n naught to n prime naught. Making a good guess. Unfortunately, there is no general way to correctly guess the tightest asymptotic solution to an arbitrary recurrence. Making a good guess takes experience and occasionally creativity. Unfortunately, learning some recurrence solving heuristics as well as playing around with recurrences to gain experience can help you become a good guesser. You can also use recursion trees, which we'll see in section 4.4, to help generate good guesses. If a recurrence is similar to one you've seen before, then guessing a similar solution is reasonable. As an example, consider the recurrence T of n equals to 2t of n over 2 plus 17 plus theta n. Define on the reals. This recurrence looks somewhat like the merge sort recurrence 2.3, but it's more complicated because of the added 17 in the argument to t on the right hand side. Intuitively, however, this additional term shouldn't substantially affect the solution to the recurrence. When n is large, the relative difference between n over 2 and n over 2 plus 17 is not that large. Both cut n nearly in half. Consequently, it makes sense to guess that T of n is equal to O of n log n, which you can verify is correct using the substitution method in this exercise. Another way to make a good guess is to determine loose upper and lower bounds on the recurrence, then reduce your range of uncertainty. For example, you might start with a lower bound of T of n equals to big omega of n for recurrence 4.11. Since the recurrence includes the term theta n, you can prove an initial upper bound of O of n squared, then split your time between trying to lower the upper bound and trying to raise the lower bound until you converge on the correct asymptotically tight solution, which in this case is T of n equals to theta n log n. A trick of the trade, subtracting a low order term. Sometimes you might correctly guess a tight asymptotic bound on the solution of a recurrence, but somehow the math fails to work out in the induction proof. The problem frequently turns out to be that the inductive assumption is not strong enough. The trick to resolving this problem is to revise your guess by subtracting a lower order term when you hit such a snag. The math then often goes through, consider the recurrence, T of n equals to 2 times T of n over 2 plus theta of 1. Define on the reals. Let's guess that the solution is T of n equals to big O of n, and try to show that T of n is less than or equal to C times n for n which is greater than or equal to n naught, where we chose some constant c and n naught to be greater than 0 suitably. Substituting our guesses into the recurrence, we have this inequality: T of n is less than or equal to 2 times c times n over 2 plus theta of 1, which equals to c times n plus theta of 1, which unfortunately does not imply that T of n is less than or equal to c of n for any choice of c. We might be tempted to try a larger guess, say T of n is equal to big O of n squared. Although this larger guess works, it proves only a loose upper bound. It turns out that our original guess of T of n equals to O of n is correct and tight. In order to show that it is correct, however, we must strengthen our inductive hypothesis. Intuitively, our guess is nearly right. We are off by a theta of 1, a lower order term. Nevertheless, mathematical induction requires us to prove the exact form of the inductive hypothesis. Let's try our trick of subtracting a lower order term from our previous guess. T of n is less than or equal to c times n minus d, where d is greater than or equal to 0, is a constant. We now have this, which is equal to c times n minus 2d plus theta 1, which reduces down to T of n is less than or equal to c times n minus d. As long as we choose d to be larger than the anonymous upper bound constant hidden by the theta notation, subtracting a lower order term works. Of course, we must not forget to handle the base case, which is to choose the constant c large enough that c times n minus d dominates the implicit base cases. You might find the idea of subtracting a lower order term to be counterintuitive. After all, if the math doesn't work out, shouldn't you increase your guess? Not necessarily. When the recurrence contains more than one recursive invocation, if you add a lower order term to the guess, then you end up adding it once for each of the recursive invocations. Doing so takes you even further away from the inductive hypothesis. On the other hand, if you subtract a lower order term from the guess, then you get to subtract it once for each of the recursive invocations. In the above example, we subtracted the d constant twice because the coefficient of T of n over 2 is 2. We ended up with the inequality T of n is less than or equal to c times n minus d minus theta of 1, which we readily found a suitable value for d. Avoiding pitfalls. Avoid using asymptotic notation in the inductive hypothesis for the substitution method because it's error-prone. For example, for recurrence 4.11, we can falsely prove that T of n is equal to big O of n if we unwisely adopt that T of n is equal to O of n as our inductive hypothesis. T of n is less than or equal to 2 times big O of n of the floor of n over 2 plus theta n. The problem with this reasoning is that the constant hidden by the O notation changes. We can expose the fallacy by repeating the proof using an explicit constant. For the inductive hypothesis, assume that T of n is less than or equal to c times n for all n values that are greater than or equal to some n naught, where c and n naught are greater than 0 and are constants. Repeating the first two steps in the inequality chain yields this, where T of n is less than or equal to 2 times c times the floor of n over 2 plus theta n, which is less than or equal to c times n plus theta n. Now, indeed, c times n plus theta n equals to big O of n, but the constant hidden by the O notation must be larger than c because the anonymous function hidden by the theta n is asymptotically positive. We cannot take the third step to conclude that c times n plus theta n is less than or equal to c times n, thus exposing the fallacy. When using the substitution method, or more generally, mathematical induction, you must be careful that the constants hidden by the asymptotic notation are the same constants throughout the proof. Consequently, it's best to avoid asymptotic notation in your inductive hypothesis and to name constants explicitly. Here's another fallacious use of the substitution method to show that the solution to recurrence 411 is T of n, which is equal to O of n. We guess T of n is less than or equal to c times n, and then argue that the recurrence T of n is less than or equal to 2 times c times the floor of n over 2 plus theta n. which is less than or equal to c times n plus theta n, which is O of n. Since c is a positive constant, the mistake stems from the difference between our goal, to prove that T of n is equal to O of n, and our inductive hypothesis, to prove that T of n is less than or equal to C times n. When using the substitution method or in any inductive proof, you must prove the exact statement of the inductive hypothesis. In this case, we must explicitly prove that T of n is less than or equal to C times n to show that T of n is equal to O of n.